Okay. Hello. I'm just making sure everyone can see. You don't like this video bit, right? Yeah, that's your problem. Get that up. Okay. Okay, LinkedIn's happier now. We'll give it a few minutes before we continue. Make some notes for me to solve after the stream. You should be able to hear me. Do you hear me? Should be recording just fine. Audio should be good. Let me check. I think the audio bitrate should be coming through just fine. That's me. Okay. We'll start. We'll plug into LinkedIn in like 2 minutes, and then we'll talk more. Okay. I wonder what the delay for all these are. Okay. There's no background sound at the moment. It's just my voice. So we pushed to LinkedIn. Hopefully everything goes well. Let me see if we can post some links in here. Post the YouTube link in case it's delayed. Okay. This, in case LinkedIn gets too slow, you guys can join us on YouTube. Okay, we got about 10 people across 3 different platforms. Welcome. I'll probably repeat myself in a moment as we welcome some new people who are joining. But thanks for joining this stream. We'll begin in a few minutes. I am Andrew Wilson. I'm also go by FPGA Zealot on some various social media. We have a sponsor stream from Altera today looking at their FPGA AI suite for the Altera Agilex 7. While we wait, feel free to introduce yourself in the chat, talk about your interest in AI acceleration for FPGAs, what applications you're interested. And then we'll see if we can discuss those as we look into how Altera implements AI acceleration within their Agilex and Aria family. Oh, we have a subscriber. So today with the FPGA AI suite, we're going to be mostly going through the demo for the Agilex 7 SoC development board. And that's mostly looking at taking their pre-built FPGA image or their SD card, and then running it on the hardware, then taking something from the OpenVINO model zoo, compiling it, doing quantization for the FPGA AI accelerator implementation, and then running through some of their examples. We'll try to explore some of the build scripts, some of the options as we go through, but hopefully we can have a little bit more fun interaction for this. So some disclaimers. This is a sponsored stream from Altera. I'm grateful for this opportunity. I am not employed by Altera. This is mostly kind of like as a hobby. I do not offer official support for these products. I am not FAE. This channel is for information purposes only, and these are my opinions. Okay. And yes, you can look for FPGA Zealot on YouTube, Twitch, Twitter X, wherever you want. Feel free to follow and continue these conversations. There's also a Discord link in the description if you want to have more discussions about FPGAs in general. So, if you're just joining us, today we're going to be looking at the FPGA AI suite provided by Altera or Intel, depending upon what guide or documentation. That the name is maybe a little bit interchangeable at the moment as they transfer to being mostly Altera in the future. Today, we're not going to be looking at much of TensorFlow or PyTorch. Maybe in a future video we'll look at how you can do a basic network in those systems and transfer it over. We're mostly looking at the AI suite architecture and kind of the graph compiler, then running it on the FPGA, the full hardware implementation today. And there are a few different ways the FPGA AI system can be integrated into the FPGA. Today we're going to be looking at the SoC system, which is the bottom right. But if you have a popular way is going to be the PCIe, which is what you're going to be doing mostly for a data center level application. And so the first three implementations are probably going to be leaning more towards kind of data center application. While the last one is going to be more of like working with the edge, or like a embedded system that's on site or something like that, or within a car. And we're going to be looking at the SoC, which is actually a very interesting one, much more complex in the sense that you need to you own the Linux image on the ARM processor as well. And we'll go through how that Linux image is built a little bit today. So the first thing we're going to be looking at is the FPGA IP core and general architecture, and kind of how you can define that IP core within the system. And then we'll look at how the FPGA AI tools build it. So now we get to go actually. So we're in a Linux subsystem within Windows. I don't think I can actually. Can't actually zoom in. Oh, we can zoom in. Oh, that's great. So we're actually here. we just have a Cordello work. If you follow the instructions, okay, we'll jump back here. If you look at the guide for the SoC design example, there's a whole talking about setting up your environment, installing the tools, and generating a work directory. So here, let's pretend I have an existing work directory. We're going to source, and ignore my weird directories. This is me just trying to solve some hard drive space. And then we're going to go open Vino. We're going to set up that. And then we're going to source. And I think, okay, so now we have sourced the proper systems. And now here there is a Cordello work sh file that will get us ready to running the scripts within the system. So now we're going to go open up Quartus, and I just want to show you the example project that we have running. It's over here. Oh, this is gonna take a minute as we as it opens up. It's a little bit slower. Well, it's also a big project, so we're gonna go ahead and open the project so we can look at the IP core. Otherwise, we're going to look at the build script. So if we go back here, for building the FPGA, there is a Python script, and you're going to specify the example design and the architecture you want to target and where you're building it. Not sure what the N is. If you build your own bit streams, you can have 10,000 inferences. Okay, so you can do about the main license just fine. Okay, cool, that works. So let's go look at where that script is. Okay, so can I just, if we just do this, will it open it up? Nope, that worked like a touch. Okay, that's still coming up. So let's look at this build script while we wait. So this build script is basically targeting whatever development board you're looking at. And we have a few additions. We're looking at the SoC. I think we're doing the S2M preset is what we're building for our hardware. But there's also a lot of other examples here that you can look at for how they build their environment. I was curious about Neos 5 software, so I'm gonna see if I can find that real quick. So for the ED4, okay, it checks it's in the path. It must be built somewhere else. Oh, yeah, not sure it's actually built. Okay. While that opens, I actually have kind of like a pre-built little diagram. So this is kind of our example SoC system. We kind of have it split into 3 different platform designs. And we have the hard processing system, the DLA kind of AI pre-core, and then the external memory. Okay. And we can look real quick, but basically the system is we have the Linux on the left, and it's going to take data from its DDR modules, transfer like your inputs to the IP core in the middle, and I assume we're using the external for transferring as we process the network, transferring data in and out of that, depending upon how the network handles that, which can be, like intermediate data as we go through the network or coefficients later. Okay. So here is the full design. Let's kind of focus on the interesting part here. So we have our top system, which contains the HPS, the external memory, and the DLA IP core. And I opened the HPS one, so we'll see how long that takes to open. And then we'll open up the DLA one, which is the interesting one. Okay. And honestly, the platform designer just has a lot of utility cores to handle the data moving back and forth, and allowing the Nios 5 soft processor to configure the FPGA AI P core. So let's kind of look at how that architecture is defined. So if we go, this is a link in the description, and if we go to where we generate our design, there is the FPGA AI Suite compiler reference manual. And when you go here, we can look at specifically the FPGA AIP core. And I wish I could have the links to show that real quick. We'll look at that real quick, and I'll show you how it selects an architecture. There's a lot of files in a lot of places, and I'm trying to make this easy to go through. Okay. Yeah, that's opening up. We have the unlicensed, licensed IP core. So the IP, the actual FPGA AI core inside your system is defined by an architecture description file, and this determines how many resources it uses, the latency, the bandwidth, the performance of your IP core. And this is assigned for each different FPGA with what you want to optimize. And in this link right here, you can find ways to generate this architecture using, all the LUTs, all the DSPs, all the memories. You can choose a certain percentage of the design, and if you want to have any pre-processing or post-processing within your design, and talk about and optimize this for exactly what you want. And I still need to go in and dig through all the options here. There's a lot that you can do to configure this. But to get into the design, to be able to use the if you want to get in and be able to test new AI inferences, well, you can go ahead and do that with the pre-built eval designs. Okay, here we go. It came up. So this is what I wanted to show for the system. So we have a Nios 5 processor, and then we have the AI core. And then we have basically data moving in and out. And for the IP core, we have an architecture specified. We can select a different architecture and be able to reference it, and it will change how much of the resources of the FPGA and the performance of our core. And hopefully in a future video, we can go look at that. And using this Python file, we can go build the evaluation examples. And you can either build the licensed version or the unlicensed version. They should both work on the eval board. So we've already gone through that process. We have that built, as you can see right here. Let's go ahead to the next step of putting Linux on the system. Those are the links for the various things. We can talk about this real quick. So they actually have the address control mapped out for the IP core. So if you want to be able to control this through a different system, you can go ahead and look at the controls for here to be able to control how the FPGA IP core works during operation. Okay. If you're joining us, I would just like to say this is a sponsored Altera stream. We're looking at the FPGA AI suite. We'll go back up real quick. We're looking at the Altera FPGA AI suite tools for the Agilex FPGAs. I go by FPGA Zealot, and I'm kind of just wanting to talk about FPGAs in general and trying to explore more of these advanced features. If you have any questions, we can go through them. Leave them in the chat. Latency is a little bit different for YouTube and Twitch and LinkedIn, but I'll try to keep up with any questions that are posted. So right now, Yusuf is asking about the Python script. The Python script, you can select which architecture you use. So to talk about what Yusuf is talking about does this Python script control what the IP core looks like, how many resources it has? It does. And that's this section right here. So if we go look at that address, which is going to be example architectures. So we're going to cd our change directory into Cordella root. And here we have example architectures. And we have ARIA 10 architectures, Agilex 5 architectures, Agilex 7, and Stratix 10. So for our example, what the tutorial talks about, it uses this performance architecture. And we can go ahead and cat out the performance architecture. And we scroll to the top. It talks about the different vectors, stream depth. Let's see where's like filter depth. Does it list like the actual resources it takes? So let's try the performance max one and see if it's anything different. Yeah, that's double memory there. Has a lot more vectors and resources. And it has more C vectors. So, yeah. If we want to look at this, it also has more additional configuration or different modules in the network that you can utilize. Is there another? Let's see if we can look at a small one. If we want to look at the AGX 5 small, no softmax, we can look at something like that. And we can see that it's much smaller when it comes to the depth, the vectors, and the output channels. And this is a way that you can configure your performance, utilization, and latency of your IP core. You can also generate your own architecture depending on the exact system you want to do. So how you guys seeing here? Okay. Want to be able to see more? Do that. Okay, that fits a little bit better. I made the Altera logo a little smaller. Okay. So we're going to look at the next step, which is building the SD card image. This is a little bit more complex, and I just want to hit a few key points here. I just want to talk about meta packages, local configuration, and kind of the build script. So we're going to go back to here. We're going to go to the runtime directory. So we're in the runtime directory inside our kind of our main build directory here. And this is, I don't like that view. I think that should have been better. Maybe it doesn't like, it's that whole pokey thing that jumps out. Okay, here we got actually 2 rows now. Bring this one over. Make this a little bit taller. So there is a create HPS image here. We can just look at this from the here. And this is a bash script that kind of goes through. We're just going to look at the options here, usage. So this is going to, it looks like it can build the example design if you want to, but this is about building your Yocto SD card image or updating your SD card image with a new FPGA image. And this allows you to get the main runtime files for your AI inference acceleration and just add them to the SD card image. We'll look at that more in detail, but I wanted to go into the build Yocto. Okay, capital Y. So we have layers here. So the layers are kind of these build these make and build scripts for specific things in your Linux. And so for like the recipes, anything useful here, this builds like U-boot and the other systems. There are other layers located in the system, but if you wanted to add your own layer right here, we could potentially add your own layer, reference it, put your own recipes in there for your own files and whatnot, and then have that go into your Yocto Linux. I'll hopefully have an example of this in a future video as we look at doing some Python utilities within the system. And then inside the build directory, if we go to the config directory right here, we have the layers. So it shows you the layers that are being referenced. So we have the main layers that are in the build directory. You have the 2 layers in the FPGA AI suite to get everything we need. But there's also a local config, and this is where you can do specific installs. Let's see if there's a good example here of what you want to add to your system. Right here, here's some like good examples. So we can add these image features to get additional binaries in our Linux image. So like this has debug tweaks for development. Yeah, root access has a blank password. So there's different systems you can add here, and it's relatively easy to modify your Linux image. It does take a really long time to build it, depending on how many processors and DDR that you have, but it can be very useful. So once you see, where's the image come out? So we go to build release right here, right? Where is it coming out somewhere else? Can't remember where the image came out. Okay, so we're just going to go to where the examples are, right? So if we go check out demo and we go to ED4, this is where we have our Agilex 7 SoC. And if we go to the SD card, these are our kind of our most important files. So we need the WIC, the WIC file, that's your SD card image, and then the JIC file is your FPGA flash. And using the JIC to program the FPGA flash, and using the WIC file to program the SD card, we can get a working demo. But that's one step. We need to go on to the next step. So if you want to look into how you program the system, there's information within this tutorial. But I think that's really it. Let's go ahead and watch it boot, and then we can talk about how we're going to load in a design zoo. Okay, so we're going to bring up... Let me bring up a UART interface so we can watch it boot. Okay. And let's see. We're gonna clear the buffer, go into terminal, and this is going to be font. We're gonna make it bigger. Okay. And the deploy images. Okay, once it's built, we can go look at where the deploy images are. Thanks. Time off. I'm gonna let this boot so you can see what the boot is. Actually, let's move this to app. Move this to the middle so you can see what's happening. About there? Yeah. Okay. So we just log into the root and we're good to go. The IP is connected and it changes IP address every time it boots up, just because of what the DHCP gives it. But we can go ahead and SSH into that address. We'll do that later when we need to transfer over a model. Someone was talking about where the deployed image is, and I just want to make sure we go look at that real quick. Deploy images. There we go. We have, is it package the image? Okay, we have that wick here. I wonder what it does to change it. Also, it's supposed to generate the JIC file, and I wonder where it does that. Okay, but that's where it... Thanks for showing where that is. Mike, there is the FPGA running in the background, but you shouldn't hear that, so you should be fine. I can get my mic closer so you can get a little better. Okay. So we can start going to more of the interesting parts and actually running AI networks. So thank you for hanging in for the past 30 minutes. So we're going to actually get to running the different models onto the system. So we're going to compile the suggested model, and then we're going to go look at some new ones. So let me close out of this real quick. I just want to make sure this isn't running in the background. Okay. So when generating the compiled systems, they want us to use the ResNet 50 from a TensorFlow. Actually, I should say hi to new people. Okay, jumping back up here real quick. If you're new and joined the stream in the past 15 minutes, welcome. I'm FPGA Zealot, and today we have a sponsored stream from Altera, and we're looking at the FPGA AI suite. You can find this on LinkedIn, Twitch, or YouTube. We're trying to kind of walk through the demo and demonstrate how the system works in real time, and kind of looking at some more of the specifics within the system. Feel free to ask questions in the chat, talk about what you're interested in with AI within FPGAs and how that acceleration could be useful in data centers or embedded systems on the edge. Feel free to add those comments. So now we're going to go and back to talk about how do we compile one of these zoos for the appropriate system. So going back to preparing a system, they want you to check out the appropriate model and then download that model. So we're basically going to kind of do this from scratch. Let me see, I have the commands here. We can walk through the commands separately. Okay. So we're going to go through the process of getting the system up and running. So in the demo, we already have, I think it's just the models. Right here. I've lost. Interesting. I haven't had to actually download that Zoom. That's probably just the example. You can look through things. So we're going to use this downloader and converter to get the system prepared for the compiling to the FPGA AI core. So we're going to look at doing it in the stream. Okay. So we download ResNet. And now we're going to convert it. After it converts, I want to see if we can get some more instructions for here. But this, it looks like it's using... Oh, it looks like it's converting it to the different floating point formats. Oh, it's converting it to an IR. So the IR is an intermediate representation, floating point 32. So now we have floating point 32 model of it for that the DLA compiler. So this is probably how you take a TensorFlow or PyTorch or whatever and make it into the same format that the compiler can understand. So we're going to go ahead and go to that stream directory and go to floating point 32. So we just have the binary and the XML file that probably describes it. So the next thing we're going to do is we're going to compile it. We're going to compile it for the benchmark. So there's like a streaming version and a benchmark version. So we go back here, compiling the graphs. This creates the ahead of time, the AOT file, that helps your IP core know what to do with the binary. So we're just going to be, we have two formats. One is for doing the memory-to-memory variants, and the other one's doing the stream-to-memory variants. This is for the benchmark utilities. You can see the true performance of the system, and this one's just going to be like kind of a real application example. But let's go ahead, run these, and I want to show you some cool stuff that comes out of it. So we have a model analyzer report that we want to look at, and then after compiling, we can look at some dot files that explain the flow of it. I'll turn off the FPGA. So we don't have the FPGA fan in the background, so you can hear my mic a little bit better. I need to find a way to put the FPGA in kind of a sound dampened area. Maybe put like a little barrier between me and the mic and the FPGA. Okay, so we finished the compiling. Let's go ahead and look at the files that are in this directory. So the model analyzer report will display the relationship between the layers in the OpenVINO graph. And is there any unsupported layer chains? Okay, there's nothing that's unsupported. There's nothing that's extra. But we can go through and see each of the transposes and whatnot. This is also done in the... Which one is it? It's going to be that one. I think to be this one. So if we want to preview this, probably hard to see, but this is the network and the different functions that the system is doing with our data and our coefficients. And that's described in this report as well. But there's a little graphic that explains the system. Okay. Any other useful information? Okay. Let's go ahead and build the streaming system. And you can see this overall gives us the expected performance for our system. And we'll go ahead and do the DLA benchmark on the FPGA in a few minutes, and we can show how that works. But this is kind of our expected performance for the system. Okay, so after running these, if we go back up to demo, we now have a bunch of binary files. These are some other ones I've built, but we have the ResNet Performance B1 and the ResNet Performance No Folding. And the no folding is for the streaming interface. We then can copy these to the FPGA and run them. Okay, I guess we'll take a moment to look a little bit more at the DLA compiler. So, when optimizing, when preparing a model, right, we are using this DLA compiler, and you saw that we ran it for like the performance testing, but we also ran it for the streaming interface. And there should be a way that we look more into the DLA compiler. Oh, this is the AOT file. So if we look at the, it's not what I want. Okay, line option. Here's where we go. So if you want to look more into how the DLA compiler works, you can go ahead and look at the compiler reference manual. And there are inputs, outputs. You can look at different reporting. That if you want to see how your AI network would be transferred to the IP core. Anything interesting? Yeah, what's the folding option do? This option sets folding the compiler first convolution network to be executed on the FPGA device. Okay, so we can take the folding of the first convolution and we can choose if it's having host or the FPGA. In this situation, this is an example, the folding option is 0. So it must be happening on the processor. Okay, architecture options. That's just targeting, optimization. I guess the compiler can be used to make the architecture, so there's different options there. Okay, and this is how you can look at the dot file if you want to have it as a SVG file. And then the analysis report we're looking at that's giving us information. So, reference manual is great, tells you how to do the commands, how to get some more information about how you can optimize your network when compiling it for the IP core. So next we're going to actually move to executing this on the device. And what files are important and what's being run on the system. If you're new, thank you for joining us. This is a sponsored stream by Altera. We're looking at the FPGA AI suite that allows us to take neural networks and quantize them for IP core within Quartus that will run on the FPGA. This helps, you can optimize for power or latency or working on the edge. So there's a lot of flexibility in how you execute your AI network in this situation rather than the fixed operation in a processor or a GPU. You have a flexibility in how you implement the design. So far, we have gone through the FPGA architecture. Kind of how we build a Linux image for the SoC, how we can take these networks and compile them into special binaries that we then send to the FPGA device to run on them. So now let's go look at working on the device. So excuse the fan sound. We're going to be turning on the FPGA again, and it's going to be a little noisy. Okay. Watch it boot again. Okay. Let's answer some questions in the chat. Yes, if you have any questions, want to discuss anything, feel free to input chat. I understand this is a lot of when you implement AI on FPGAs, there are very many layers, right? You have the hardware, we have the Linux OS, whether that's on the device or host system. You have your network, and then you have the tools that are compiling that network down to your FPGA level and then executing it. So there's a lot of different layers, and it's a lot of information that go at one time. So we're going to go ahead and connect to this device. We have the same IP address, luckily. So we're going to pull up mobile Xterm. Let me set this up so that we can communicate with the system. Okay. And about there. Okay. So let's look here. So we added this ResNet folder. It has a bunch of binaries. These are all different networks I was playing with. We have a bunch of sample images that come with our demo design. And these are just basic test images to run with the system. And you can't really see much. But we can just go this way. These are binaries, and we have our test images here. Then app here. This is everything we need to run the system. So we're going to go through this step by step of how we set this up. So we need to restart the UIO drivers, so we have those set up. And now you should see UIO 0, 1, and 2. Oh, you can't see it. How dare I talk about this when you can't see it? Okay. Something like that, right? Okay, so we restart the UIO devices, and we can list them. We have 0, 1, and 2. Next, we're just going to reference what systems, images, and whatnot we're running in this system. And we have the binary that's from the DLA compiler, our sample images, and the performance system. And then we're going to add a reference to our DLA app, so it knows how to run these files that we have here. And we're going to run the DLA benchmark. And we can kind of talk about what's happening here. Okay. Why it runs. So we're running the benchmark. We're doing a heterogeneous system with the SoC CPU and the FPGA. We have the ground truth specified within the image directory, and we want to estimate our performance. And it goes through and loads the system, loads the OpenVINO, make sure we have the FPGA, make sure we have the processor, and then it will run the system. And we can see here, this is estimating 27 frames per second. Now, if we go back here to our previous system, this is the estimate that's provided by the DLA instances, and it says 150. So I wonder, this 65. There's a latency. Did we talk about latency here? We talked about frames per second per megahertz. So depending upon our megahertz that we're running at, we may not be running at the max. Okay, it's talking about 500. How fast are we actually running? What's the system clock? Okay, we're running at 200, and we're getting 65. If we ran at 500, we would get 150. So we could definitely run the system potentially faster as long as we place and place and route and get the correct timing. Here, we can get the estimated performance with 500 megahertz, and that matches this number right here. So the benchmark and the compile code are the same. So we're running ResNet. This is doing an image identification. Let me see. We can go look at that folder real quick. So here are the basic images that we're running through our system. And it's just identifying this. And if we look, let me see if there's anything useful on this system. And these are the numbers that match with 0 through 9, right? So this is what we should expect for each of them. I assume some, okay, yeah, it repeats. So we're identifying what's in the image. Okay. So that was the benchmark. We can go ahead and talk a little bit more about the benchmark here. and we can use it to identify how our network would operate in a real system. And if you want to look more at the benchmark application, feel free to look at the PCI design user guide. I guess goes more into it. Does this one? I don't. Okay. Using this right here, test and evaluate, you can look at what that system is doing. Okay. So next, we're going to look at a streaming option right here. So the S2M mode. This is the streaming demo, and this allows us to show what happens if you have a constant flow of images in your system. So there's basic example. They want you to run the inference stream and the image stream, and that will allow us to produce this information here. So mine looks more like this. So let's bring it up. That's going to be on the next page. Where it has the class idea and the score. Okay. So let's go ahead and look at what these systems are. So we're going to cat the streaming inference, that the SH. Oh no, it's the run. Okay, we're going to inference stream, and let's nano it. Run. Nano not found. Okay, so just do. Okay. Basically, this is running the streaming inference app with a model that's expected. Oh, we may need to copy that model over. I don't have that here. And the architecture and the device. Let's make sure I actually have that. Okay, we don't have that one here, so let's. FPGA. Here we go. We have the directory, and we're going to go to demo, and we have this no folding. We're going to bring that over here. No. Let me pin this. There we go. There we go. And we're just going to carry that over here. There we go. Should be way faster than that. Okay, so now we have the ResNet 50 no folding binary, and we should be able to run. Oh, actually, let's look at the streaming. We want to look at the streaming first tab. Did I not? Should be added. Okay, it's ready for the input image. So here, we're going to go ahead and source the run image string. Okay. So we're running constantly through the images. Let's go ahead, split this into two terminals. And balance that out a little more. There we go. A little more. Okay, and this is us running the inferences back to back. that is the basic demo. We'll let that run, but I want to look at some more examples. So if we go to the zoo, get this set. We want to look at, we have different examples we can look at. And we can see the complexity and the size. And we have Intel verified ones and then a bunch of classification ones. And we can talk about all these different ones. And YOLO is probably a really fun one to look at later. What I got working was the age gender recognition system. This is a relatively small one, and it's really easy to build. And so let's go back here and show how we go about getting our own system. So going back to the OZM downloader, right? We specify the name. In this situation, we want to use age gender 13. And this will download that pre-built one. So we have a ton of AI networks that you can reference and start working from right now. So we download it. Now we're going to convert it into that intermediate representation that will allow us to use the DLA compiler. Once again, we just change the name of our ResNet function and use this. Put it again. There we go. Since this is already an Intel one, they must have it already set up. So we go to stream, we go to Intel, we go to FPGA32. We have the bin and the XML. This one's actually cool because we actually zoom in on the dot file. So we're going to go ahead and compile this for the benchmark. Let's just call this age gender recognition. Right? Okay, and then we just need to go to XML, and we need to reference the XML here. You can do that with tab complete. There we go. Okay, so it says the throughput is almost 3,000 frames per second. Okay, let's go look at the dot file for this, which is probably the most interesting thing. But did you see this right here? 5 frames per megahertz. That's pretty impressive. You could run this at 1 megahertz and still get. Oops, sorry, I need to rerun it. So here is the dot graph. This one we can actually zoom in on. Right here. And we can see that we have different convolutions, the max pool, a ReLU, convolution, ReLU, and you can see how the network is built, where the coefficients are coming from. So these are all our parameters that we trained upon are located in these boxes right here. And the FPGA AI core is going to use this function with these coefficients and perform the networking option. So this is kind of every step that's happening in our FPGA AI core. It's pretty cool. Anything on the report? No, I think that's about it. Okay, so let's go ahead and do a benchmark of this. Okay, let's go back here. So this has been running nonstop. Ran 18,000 identification. So we're gonna kill stream, and actually, what did this run? That was the image stream. This is the inference stream. Okay, let's go back to single terminal here. So we want to look at. We're gonna look at. What is it? Age gender right here, the age gender one. So let's go back up to the benchmark right here. So what we're going to do is we're going to remove the ground truths because it's not going to work that way. We're going to use the same image directory, but the compiler model is going to be different. So we got to go switch that out. So to our echo, that's the compile model. We're going to do the age gender. This one right here, and then perform the benchmark again. And so the benchmark on the age gender representation with no ground truths, it converts all the images from 224 to 62, but this says that using the benchmark we should get around 2888 frames per second, assuming 500 megahertz clock. Our system is 200, so it is achieving 1600. And if we go back here, that was the final throughput. So if you do the compile and you see this option, it should match what you can achieve. So that's kind of the different demos that we have for this system. So there's some next steps I want to talk about. But first, thank you if anyone's joined since last time. This is a sponsored stream from Altera. We're kind of going through the FPGA AI suite, trying to just explore the basic tutorial. And I do various other FPGA related content. You can find me on YouTube, or Twitch, LinkedIn. But I'm so grateful for this opportunity to talk about the FPGA AI suite with the Agilex 7. And we want to be able to go through these examples and make it more user-friendly for people to pick this up, because it's a rather complex system. We can kind of talk about this. We went through the FPGA architecture, which is using a good portion of the FPGA to transfer data from the DR to your FPGA AI cores. For this system, we have an SoC, so we are using Linux, and then we pick our model and compile it specifically for our system. And we've gone through that demo. Feel free to look at the recording previous here to see how that demo works. But the next steps is, how do we use this for our applications? And I really want to look at that in future streams. How do we do a custom architecture on a custom PCB, where you don't have necessarily have the same interfaces as the eval board, or you're using a different FPGA with a different side? How do we get the architecture working for those systems? How do we get the data in and out? In this example, we had very basic sample images, and we want to be able to have those images be flowed from a data stream, whether that's a webcam, PCIe, Ethernet, some LiDAR, radio, or something like that. We have information we want to come in. We want to be able to compute upon it and act upon it. So I want to be able to figure out some new data flows and be able to explore how do we import our own neural network based upon those flows. If there's any other applications you want to see, please leave them as comments. And we'll be able, hopefully I'll be able to try to find some examples that fit that. This was a very basic tutorial trying to follow their flow. The future examples will probably have official GitHub repositories that kind of walk through how it works, and so something you can walk along. It's hard to run this from A to Z. It takes several hours to do the FPGA image, several hours to do the Yocto image. So it's really easy to start from an eval board with the pre-built image, and you can get a majority of the FPGA AI suite working on an eval board to figure out what you need for your application. So we're probably going to look at that first. How do we effectively use an eval board for more of a custom neural network or data flow, but using the existing bitstream and Linux image that it has. So thanks for joining. I think that's going to be it for the day. There was a lot of content, so feel free to leave questions and to join the Discord to talk more. I'll stay on for like another 5-10 minutes to talk through questions. I just got that grid. Okay. So Yusuf, you're asking how do we, through the development steps, how do we test and verify each step? That's a question that I'll probably have to work with myself, because with, okay, we're still streaming correctly. Looks like things have, interesting. Everything says it's happy, but everything seems to be delayed. Okay, I'll answer a few questions and I'll end the stream. How do we verify each step? I mean, when we have the FPGA image, how do we verify that the IP core works? You're going to have to go through the flow, have the existing Linux image, use an existing neural network to be able to test your custom architecture. But then from there, you're going to have to use existing parts to test what you are developing on. I don't have any good examples at the moment because we just walked through like the pre-built tutorial, but hopefully as we get more user-based examples, we can work through it. Okay. So that is... Okay. Look for a stream in 2 to 3 weeks. We're going to try to look at using a USB webcam with the SoC and be able to feed images into the neural network. And hopefully we can walk through these steps a little bit better. I can tell you by doing this stream, feels like a lot of material to cover in any amount of time, and that if you need a training or webinar or something like that, reading through documentation, going through tutorials is going to take a little bit of time. But once you have the eval board and you have the system, the example system, it takes just a few minutes to start changing out different neural networks and see how effective they are. Well, thank you for the stream. I will see you in the other